Hello everyone. So this Google Summer of Code, I worked on supporting 64-bit pointers in RISC-V LLVM 32-bit backend, and like everyone asked me, so what's the need of this? Why you did this? So let's start with some background. So there's a effort from Professor Taylor at University of Washington. They are trying to they already taped out some silicon for version 1 where they made a GPGPU based on RISC-V. For the version 2, they want some programming capabilities and those stuff. So we wanted to support 64-bit pointers to access DRAM so that we can have all the good things about what we can get from a 32-bit chip, and we can access the 64-bit memory, 64-bit addressable memory. So we thought, okay, let's do it. So how to do it? So we thought, okay, just add two instruction, a load and a store for in the new instruction, so that we can just have 32 halves of the address in both instructions, and we can just easily load them, store them. This sounds pretty trivial, right? So I asked, okay, so how do we add instruction in the LLVM backend and those simple stuff, just add an instruction in LLVM backend. So there's it's simple. It's pretty simple. You just need to pass the legalizer, then just do simple ISL and it's done. It's just simple pattern matching. Legalizer should never trouble you. But this is what I saw. This was not what I was expecting. Yeah, so the main issue was that the legalizer is a silent dragon. It won't say anything. You can just easily pass with that. It won't hurt you. It will never hurt you. But if you will poke it, it can be tragic. So the thing was that we had 64-bit addresses on a 32-bit target. Legalizer always said no, we are not going to do this and that, and we had really hard time. So this talk is mostly about what are the things that you can do to just bypass the legalizer, and I have a poster session where I'll discuss more about that, what we exactly did, what are the things that we exactly tried to just get around this dragon. Cool. So initially we had 64-bit addresses. We did some hack. We are like, okay, the 64-bit address should pass the legalizer. It passed the legalizer. We are so happy. Okay, we are going somewhere. We're going somewhere. But then when the store and load node see, okay, this is a 64-bit address, the legalizer say, oh man, this is illegal. I need to call the police. So it's so we are failing. We are failing at the legalizer at very bad. It was awful. Then LLVM have many things for escape. So as I say, perform deck combine. This thing can give you infinite powers that you can use against the legalizer. Before at this phase, okay, I still have time. Yeah. So at deck combine, you can use perform deck. You can use this perform deck combine. It is really good. I'm really selling you this. You can use this. You can tweak the nodes in any way that you want, and it should pass the legalizer because this is the deck combine one is before the legalizer, so it's fine, right? The second thing is replace node results. So when you are stuck with type legalizer, you just need, if you are stuck with type legalizer and your issue is that you just want to change the return type, just use this. It's awesome. It works. I've tried this. The next thing that I'm selling today is lower operation wrapper. So it says when the result is legal, but the operands are illegal, then use this. So these all stuff are before the type legalizer thing. Next thing is lower operation. That is so common. In backend, it's pretty common. It's used everywhere. So this thing is used when every types are legal and you just want to tweak the way the nodes interact with each other, the node legalizer stuff. And this is how we did at the end. We had a global address, 64-bit. We just broke into two, just put it inside a build pair. For build pair, thanks to Tim, we could do it. I just have 6 seconds left. Cool. So how did we achieve it? So it was we just need to take the things away from the legalizer as far as possible. So we did that, and I'll see you at the poster session because my time is over. Thank you.